Well, good morning to everyone, or good afternoon, depending on where you are in North America. My name is Gloria Warland. I'm Regional Marketing Manager in support of our 5G business unit. And on behalf of Viavi, welcome to our second session in our Managing Uplink Interference Best Practices series. This session will be covering mid-band inter-cell interference. The session is being recorded. All lines are on mute to be respectful to everyone who's on the call. The recording will be available on our website in a few days. We are monitoring the question and answer session. You can see this option at the bottom of your screen. So jump in anytime with any question that you may have as we're presenting the material today, or if you have a request for some additional information. Our speakers today are Eduardo Inzunza, who is in our product management group, and Dan Schmedtje, who is a domain solutions expert. I'm going to turn the session over to them now to get us started, and take it away, Eduardo.
Thank you, Gloria, and hello, everybody. As Gloria said, along the way, I'm probably going to pause just to give you some additional opportunity for you to ask any questions you might have. But even after the session, if you have any questions, please feel free to send them over. Here, as you can see on the slide, I've added Dan's and my email address, just in case, again, you might have any questions, comments later on. Okay, so with that, we're going to be talking about this second presentation about uplink interference. As you might remember, the first session was about passive intermodulation. This session is going to be about inter-cell interference. And the next one, it's going to be about external interference. So with that, let me just go into it. What's the scope, or which are the questions that we might want to answer? One is, which are the sync and time requirements for 5G? Are they the same for LTE or different? And how is, or why those are different? And why it's critical for 5G? And as you might notice, this is going to be specifically about time division duplex, or basically carriers in mid-band which are transmitting the uplink and downlink on the same frequency, but a different time slot. And that's basically the nature of this communication mode that is referred as TDD, or time division duplex, which, for that matter, this problem of inter-cell interference is not only applicable to 5G, but for that matter, for any TDD communication. So that includes even LTE that is being transmitted in TDD mode. And as we all know, everything that it's in mid-band, it's in TDD mode. And by mid-band, I'm referring to anything above 3 gigahertz and below 7 gigahertz. Even for that matter, anything above 3 gig, it's TDD based. But we're going to be talking about why is critical, and then how these timing deviations might create problems with the uplink, specifically why we might have interference, how we can test this problem over the air, and then we're going to be doing a quick demo on how this is done with a reception that we have here at our house. And then going through the best practices in terms of sync and timing detection and mitigation process. And then at the end, I'm just going to be giving you with additional information and references. Okay, so let's talk briefly about just in general sync and timing guidelines. And I'm going to start from a 5G transport network. This is from the standards. And as you can see in this diagram, it's just depicted a network, network topology, 3 different topologies. As you can see here, we have the core of the network with 3 different scenarios. But one is the distributed RAN, actually it's 4 of them, but distributed radio access network centralized. distributed with virtualized RAN, and centralized with virtualized RAN. Now, in terms of how synchronization and timing is being distributed, first off, on distributed RAN, the core can just send that over to the hub site, if you will, or the small cell, and that is being then distributed from CU, DU, and radio perspective. And that is basically just a straight wireline connectivity between the core and the radio access network. Second is basically the same thing, but the only difference, though, is that here we have in the middle a central office, and with this central office, then everything goes remote. For example, we have, I don't know, San Francisco, or any kind of big metropolitan area, which from a CO, we have different fibers reaching out into the radios, and that connectivity, or that segment of the network, is the front haul, and that protocol that is being transmitted in the front haul, it's CPRI or eCPRI. Now, it's an important notion, this distinction that I'm going to be talking about later between CPRI and eCPRI, just because CPRI is an always connected methodology or link between the CO and the radio, whereas eCPRI is not always connected. By that, I mean that is packetized, so different packets that are being transmitted from the CO to the radio. And we'll be talking about the implications of it. Now, similarly, we have on the distributed RAN with the connection between the backhaul to the data center and then the small cell. That's being referred as small cell, and then from the small cell to the radio as front haul, and then from this data center can go into a CO into fiber on CPRI. So anyway, this is just to give you a sense on just different scenarios and different segments that the signal is going to get propagated from the core all the way to the radio. And why that is important, because we have to take into account all those different jumps or segments for the time budget that we have available. So time budget, which are the requirements for that time budget? And it all depends on the services that are going to be delivered. It can be a mobile broadband, or it can be an ultra reliable low latency connection. So for that, again, taking just from a guidance from the standards, we have different latency requirements. And those latency requirements, again, it all depends. When we take these different jumps or segments based on the topology and the latency requirements, we can basically map it out. So here we have an end-to-end latency allocation. So how much of that budget can be in each of those jumps? And I'm just going from, in the last section here, from right to left. I've been sending my signal from the core all the way to these different components, the CO, DU, RU, and then the mobile services right here. So as you can see here, just this is an example that the standard is giving us in terms of all these different timings that we require all the data to get transmitted on. So with that in mind, then the standard says, okay, so having all those timing requirements into consideration and the goal of the maximum latency that should be expected, then it was defined what's going to be the time allocation, the time deviation on the radio. And let me expand this a little bit. So these are the time and frequency synchronization aspects defined by the standards. And as you can see here, for anything TDD related, which as I mentioned before, so basically LTE or NR that we're going to be talking about, the maximum deviation based on a primary reference clock, it's 1.5 microseconds. So this is very important, because once anything it's deviates more than 1.5 microseconds from a primary reference clock, then we are going to start to see some problems. And how those problems are reflected in services, that I'm going to be talking about that a little bit later with a couple of examples, but that basically it's going to be reflected as interference in the uplink. Just one additional note, what's a primary reference clock? A primary reference clock is defined also by the standards, and basically is being given by very stable elements. Those can be a cesium, a rubidium, and those elements, cesium, for example, that is being used by satellites, that is going to give us a very stable frequency. And that is being delivered via GPS. So GPS receivers, they have internal oscillators that lock into that cesium signal, and that's how typically those are the elements being used for synchronization and timing distribution in networks, and more specifically now here, it's being used for distribution into the radios. That's one way of doing it. Another way is by having multiple synchronization elements throughout the network. So let's actually let me give you a couple of examples. So I briefly kind of explain what's a primary reference clock, based typically on actually masers or cesiums, and cesiums are in GPS satellites, and that signal is being transmitted out, is being transmitted or broadcasted from those satellites. Locally, we have receivers with GPS antennas, or GNSS for that matter. It can be GPS, or it can be actually different type of constellations. Galileo might be another one. But anyway, we get the signal from a receiver, and that receiver into that site or that central office then synchronize all the network elements. So this is an example of just how we can have a primary reference clock into all those different network elements. The alternative that we're currently seeing, albeit more used, is not necessarily to have all those elements into the network, but to distribute that time and signal through the network. So as you can see here in the other example that I have, we have a GPS receiver, for example, that is being providing sync and timing to a master clock, and that this master clock goes into the packetized or transport network to the slave clock, and this slave clock then provides timing to what is being referred as the end application. In this case, it's going to be a radio. So again, two different scenarios, two different modes in which how synchronization is being distributed. All that being said, at the end of the day, for the radio to mobile connectivity, that should comply with the requirement of 1.5 microseconds against a primary reference clock. And I'm referring on these two different scenarios, or two different philosophies of distributing sync and timing, because if we see problems in the network of sync and timing, then we might be doing a different troubleshooting methodology based on how the sync and timing is being done in the network. And we're going to be talking about those two different cases, being done by a GPS receiver locally, or being distributed throughout the network. Actually, before I move on, let me just pause for a second to see if there are any questions that we can answer.
Eduardo, I've been monitoring the chat window, so I've got those covered.
Thank you.
I do want to say just to the whole group, this is important. This is a hard topic at this level. I think the rest gets a whole lot easier as we talk about the RF domain. But effectively, right, your choices for like older FDD networks are GPS receiver, because that's all we needed at each cell site. GPS is cheap. As sync and timing become more important in a TDD network, C-band, band 41, et cetera, you need more than just a GPS receiver. So we've implemented, not we at Viavi, but the industry has implemented PTP, packet precision timing protocol, where it uses the same GPS, but then it uses that cesium or rubidium clock to make it a more accurate system, to give us more than just frequency accuracy, to give us phase accuracy and timing. And that becomes critical as we move forward with C-band and band 41, because of the nature of an on-off system where your uplink and your downlink are the same frequency. So just to kind of wrap all this up in a package for everyone, right? Hopefully that makes sense. Eduardo, I'll shut up now and you keep going.
No, good. Thank you, Dan. Okay, so now let's talk about 5G TV. So mid-band, so as I said, everything that it's, I'm just gonna be talking about the bands being defined by 3GPP, kind of, these are a couple of examples, band 77, band 78, although, as I mentioned before, it's also applicable to anything that is being transmitted on TDD. So it can be also a 2.5, 2.6 signal that it's in TV mode. But as you can see here from the standards, everything that it's above 3 gigahertz, it's TDD, or it's time division duplex. But what is time division duplex? But simply put is the signal is being transmitted on the same frequency for uplink and downlink, and the distinction between uplink and downlink is based on time. So here's just an example. Let's say that we have a carrier 3.5 gig. Here we have my frequency power. For FDD, or frequency division duplex, we have the downlink in one frequency and the uplink in a different frequency. For time division duplex, both are in the same frequency, but as you can see here, I have added another axis. This is the time axis. So now we have downlink being transmitted in some period of time, then the uplink is being transmitted, and then downlink, and so on and so forth. So these arrangements of downlink, uplink, downlink, again, the standard defines them by a frame configuration. And this is what I'm showing right here on the left. There's different frame configurations. Actually, the frame, and I have later on, I'll describe a little bit better a frame and how is that being divided into subframes and slots and symbols. But in any case, here we have, as you can see, this is again just as an example of the slot formats. So here we have how many symbols? We have 14 symbols in a slot. And as you can see, how each one of them can have a different configuration. D for downlink, and U for uplink, and F for flexible. So the mobile operators, they have different frame configurations. How many of them? I think there are about 56 different configurations that they can pick and choose. But it's important that once that frame configuration is being defined, that should be used in all the radios. Otherwise, it's going to be a big problem, because as you can imagine, we might be transmitting on the downlink in one radio where the other radio might be expecting uplink. So certainly that overlap between two frames that are different, that have a different configuration, is going to cause a problem, a significant problem of interference. Okay, so let me dive a little bit more into a signal. So let's have just here a regular signal. Here we have my frequency and power. We have my bandwidth, can be any bandwidth defined by the standard, anyway from 5 all the way up to 400 megahertz. Here in C-band, we've seen different bandwidths being allocated. Typically, we've seen 40 meg, 60, and 100 megahertz. But anyway, here, let's say that we have a 40 megahertz signal. And again, we're looking here at signal and frequency and power. We see everything that is being transmitted out. This actually happens to be a lot of subcarriers. a group of subcarrier constitutes a resource block. And I think some of you might heard of resource blocks. That's typically how data is being allocated by a resource block. But again, it's a group of different subcarriers. Okay, now let me kind of look into the other axis, which is time. It's going to be the same signal, but that signal now it's in the time domain. And as you can see here, we have a frame of one frame in 5G is transmitted every 10 milliseconds. And that frame has 10 subframes. Now, in LTE, actually, all these was pretty said and done, and it was just one single configuration in terms of the subcarriers that I briefly mentioned before here on the frequency domain. Those were 15 kilohertz subcarriers all the time. So we always have here in LTE 10 subframes. Now 5G changes in a way that you have now options for subcarriers, and is being referred as the 5G numerology, that we have different subcarriers or subcarrier spacing. And as you can see, the first example, the first numerology that we have here is just the same as with LTE, 15 kilohertz. How many slots in a subframe? One. And the transmission bandwidth and the SSB, I'm probably not going to be talking much about the SSB, but the SSB is basically the beams being transmitted out on 5G. I'm probably going to be putting more attention here on the number of the slots and the subcarrier spacing. Why? Because as you can see here now, we have also the option of 30, 60, 120, and 240. The one subcarrier spacing that is being used typically for mid-band, it's 30 kilohertz. Now, why that is important? Well, as you can see, it's actually is wider, 2 times wider than 15, but it's going to be 2 times faster than LTE. And that is, again, important because that's how we can, from a over-the-air perspective, that's how we're going to be getting kind of more speed and more responsiveness out of the network. So here, let me just give you a kind of a picture of, okay, so we have for a subcarrier spacing, 15 kilohertz. That's my slot size. Now for 30 kilohertz, I have now 2 slots. And basically here we can have data now in each of those slots. Now, how is that data being transmitted out? If I just expand one of these slots, I have my 14 symbols that I can transmit over. And I put here different colors because each of those symbols can be configured with my frame configuration. So, for example, in this example that I'm going to be showing you, I have, and I've just used the same frame configurations that we got from the standards. So I'm going to be using configuration 0, 0, 0, 44, 1, 1, and so on and so forth. So, okay, so how does that look like? So let me just expand it a little bit. So I actually color-coded these frame configurations. 0 basically is everything is downlink. Then 44, it's downlink and flexible. This flexible is actually something that 3GPP has defined as a transition period or transition time between downlink and uplink. And then finally, number 1, it's everything, it's uplink. Okay, so that is basically how a 5G frame is constructed based on all the different frame configurations on a symbol level. So how does that look like? If we kind of have an analyzer and look into the frame, basically looks something like this. So as you can see now, we have my downlink section, my flexible section, my uplink, and so on and so forth. Great. Okay. So now, if we have my downlink, my flexible, and uplink sections right here, I should expect that all that, as I mentioned before, should be transmitted the same way from all my radios. And as you can imagine, for example, here we have a radio that is transmitting my frame, and this radio is getting synchronization from a clock. I'm just going to call it a clock because, again, this clock might be coming from a GPS receiver or might be coming from a slave clock through the network. And the expectation now is that I should keep the same frame on all the radios. So if I have another radio here being transmitted, the same is exactly the same frame. Actually, I just took the same exact traffic for you just to have as a comparison. The difference, though, is that these two signals might not be aligned. So there might be a problem, a slight deviation on the clock of this radio. Okay, so why is that a problem? Will that impact services? And the answer is yes. Why? Because as you can see, because of this deviation that I'm getting, as you can see, my downlink on this cell is overlapping with my uplink on my second cell. And that is constantly be happening, and actually can get worse if this deviation is not static, is not a specific offset, but if it keeps deviating, as you can imagine, this frame is going to keep moving, and then I'm going to have more downlink on top of my uplink. So certainly a service impact problem, because again, keep in mind there might be two different variables or two different elements for sync. One is an offset, but the other one is going to be a constant delay or delay variation that the cell might be experiencing. And why that might happen? That might happen if for example, this cell is just running by its internal oscillator, kind of loses lock from my receiver. And typically, again, just to keep it simple, these receivers are primary reference level, meaning that it's very stable. But the oscillator here in the radio, it's a secondary or even a third level. This is typically a quartz oscillator that resides here in the radio and is being running by its internal oscillator. So it's continually be deviating, and it's going to be then sending my signal that is going to be shifting in time. Okay, so again, which are the requirements for sync and timing? I'm going to be starting with the time error requirements. And again, this is for TDD. And as you can see here, it's applicable for any kind of configuration in terms of if we are aggregating multiple carriers, or if we have MIMO, multiple input, multiple output. Here, the way in which we assess that time error is with our one advisor solution, making an over-the-air test. Here we have a directional antenna, recommending to have kind of connectivity, well, good signal coming in, and then we assess what's that time variation. So here, actually, just to avoid traffic from other cells, we can actually lock to that PCI. So for example, in this case, let's make the assumption that this radio that is transmitting a signal is PCI or have a cell ID of 150. Say, okay, so we're going to be just looking into that signal. And we're going to, because that's a signal under the radio under test is coming from there, from PCI 150. So we lock into 150, and then actually we can put limits of plus minus 1.5 microseconds. These are the lines that I'm showing you right there. And this test is being done with the instrument being locked to GPS. So GPS is our reference, is our primary reference clock, and that's how we're testing the radio. And this is the time error variation. It's very straightforward, simple to do. Again, this example that we're going to be showing you is based on a C-band carrier. Okay, actually, let me just pause one more time to see if you have any questions.
There are no open questions. I've been answering them as fast as I can in the background.
Perfect.
Good
Thank you, Dan.
questions, by the way, for everyone asking the questions. These are some good, you're making me type a lot. So these are great questions.
Awesome. Okay, very good. So once we have that, we actually have automated not only the limit lines that as I mentioned, it's plus minus 1.5 microseconds, but also we have added this indicator just to have an easy pass fail notice in front of the instrument. So you will be able to know fairly quickly if the radio is within the standard. Okay, now the second concept is cell phase synchronization. That is somewhat related. And cell phase synchronization basically means that it's, again, for TDD, and is the maximum deviation that we might have between two cell sites. And that's a difference. The difference is in time error. It's an absolute timing, which is against a primary reference clock. Whereas cell phase synchronization, it's a relative time difference between two radios or two cell sites. And therefore, then here, the maximum tolerance or that it's, or the minimum requirement, I guess, is 3 microseconds. That's the maximum deviation that two cell sites might exhibit. So by that, we have two cell sites. Typically, certainly, we need to have an overlap for a good handover. So if a mobile is just going from position A to B and is going to be switching from one cell to the other. And again, it's TDD, it has a specific configuration that is being transmitted out. And I have another one on the cell that I'm just about to hand over. And it's the same configuration, but I have a slight deviation or offset between them, then I might have a problem. And that's basically that interference or that cell phase sync between two cell sites. And how we can assess for that cell phase synchronization. Well, similarly, now we used our instrument, our one advisor, and actually here we have an omni antenna just to have reception for multiple cell sites. Now, the measurement now itself is going to be slightly different because now we have visibility of multiple cell sites. And again, this is a relative measurement. We're going to be taking the strongest radio. In this case, it's going to be our primary PCI. Just like any phone is going to stay with that radio, is going to stay latched into that one, and is not going to do any handover until we get a big power difference between one radio to the other, so I can do a handover. So we're going to be keeping our primary signal as a reference, and then we have a list of multiple candidates that basically are adjacent PCIs that are being received on any specific location. So in this example, we have, again, a PCI here. It's a PCI 90, and then is being comparing that signal with the other PCIs. So I have here an example of 100, 102, 104, 202, and so on. Here on top is basically a very simple diagram. Each bar represents a cell site or a radio. And here we have also defined my limits. As you can see now here, it's not 1.5 or 3 microseconds because this is between two different radios. And it's making that test. And if it's within these limits, then it's showing that that PCI is green. It's okay. It's within the tolerance. If it's higher, like for example 204, it's actually in this specific example, it's 3.67 microseconds. So that's off the limit, and it might be causing interference. So again, it's a pretty straightforward test. Now, as you can imagine, this is not going to be just a static type of measurement, but we have to have also kind of a little bit of assessment, not only between 2 cell sites, or here in the example that I'm showing between 5 cell sites, where it can be, those cell sites might be different as we go through the network. So for that, then we have the ability to do it from a network assessment perspective. So with that, we have the ability to do a drive test and do a route map of cell phase synchronization. So here, basically, now we are going to be able to have a map, because we're going to be, again, going through multiple cells, multiple radios. And if it's within 3 microseconds, then we're going to have a green indicator. If it's outside, then we're going to have a red indicator. So here we're going to be able to get not only the locations where we have a deviation, but also we're going to be able to get the PCI. In this case, for example, my primary was 189. The PCI that was off, or that it's off, is 296. So a very good distinction between them, and a good assessment of, okay, so from a network standpoint, which are my radios that are out of sync, and I need to correct. Okay, so now we're going to be doing a quick demo that Dan is going to be helping us with. Dan?
Absolutely. Do you want to share your screen, or should I share mine?
I can share mine. Let's see.
Okay. There we go. If you could maximize that, that would be wonderful. Hello, everyone. Again, so Dan Schmedtje here, kind of backing up Eduardo, the chat windows. So what we've done is we have a system set up on a C-band radio, and so we wanted to show you the spectrum so people can just kind of see what it looks like. There are 2 distinct signals in C-band right now. We have a lower one, and the upper one, which is the one we're focusing on, has a little bit more power at our location. So you can see what it looks like from a spectrum analyzer point of view, right? This is a TDD 5G NR signal. I believe it's about 40 megahertz wide in this case. And there's your uplink and your downlink, right? For those of us familiar with the screen, looks exactly like FDD. Can't really tell the difference here, only because of the nature of the speed of the uplink versus downlink time slots that Eduardo went over. Not able to see it here. Eduardo can be, oh, I have control. I can go to the next tab. So a quick example that we showed from the other screen is our one advisor will have a GPS input as we have it here. We will create our own timing source for us and use it as a reference signal, if you will, not really the right terminology, but we'll use it as our master clock, and then we'll monitor the SSBs to see what is the timing output of said radio. In this case, we're looking at a single sector. The PCI is 150 of the sector that we're looking at. And Eduardo was kind enough to put a distance offset. And that's important because remember, the measurements we make are relative to where we're standing. So, you know, we're taking this from a phone or a UE's point of view, is timing is different as you are farther away when you have to reference to an absolute clock, which is our internal GPS. So we put it in there. He put it in there. I didn't do this. And you can see this clock is on average about 20 nanoseconds early in time. We're not going to pull up the table, but back early in the presentation, hopefully you saw the table that comes straight out of the spec, out of 3GPP, that talks about class of service for mobility systems, both 4G and 5G in this case. Our class of service we're in today is roughly, it's not roughly, it's absolutely a time error of 1.5 microseconds, plus or minus. So a total of 3, but you can go either plus 1.5 or minus 1.5 before you become out of spec. And that's an absolute time measurement. And that's what we're showing here on the screen. Kind of boring because this one's working. It's much more fun when you can show a bunch of errors, but we don't want to do that in this because this one happens to be working. And that's the key to all of this, is this class that we're in. The table, which we didn't really go over, is a table that has that has evolved over time. The next class of service, right? I believe we're in class C. Don't quote me on that letter for these specs because I'm doing this from memory. But we're going to go to class B after that, I think. Correct me if I'm wrong, Eduardo, if that's not the right letter. And that timing tolerance, when the service provider gets there, will move from something like 1.5. I think is it 66 nanoseconds or is it 300 nanoseconds? Either way, the time tolerance will get smaller. And the reason for that would be the things that we're envisioning for the future. Connected cars, low latency transmissions. To do all of the stuff we want to do that 5G has promised, we have to have an extremely tight timing tolerance. Today, we're not there. Today, we're in, hey, this is a basic TDD network. There is a TDD LTE network, by the way. It's in band 41. Same concepts. If I want to hand off from site A to site B, sector A to sector B, I've got to be within this 1.5, not only for the uplink interference that we focus on, because that's where we see a lot of problems, but just to be able to not have that old island cell effect we used to have. And that's what we're showing on the screen. So simplistic measurement, drastically powerful, and the pass-fail limits will change over time as, you know, the AT&T, T-Mobile, Verizon's, Dish, now that, well, Dish isn't TDD yet, as they change their network to get different levels of service, these numbers will change. So just there's my really long explanation of why this really slow screen is moving. We're camped in front of it. We have 500 measurements to see, is it drifting? It's a drift clock. It's a wander clock for anyone who came from the Ethernet world, and maybe more like jitter in some cases, right? You can do both. We monitor it. So this is our absolute measurement for this site. Next tab over, which we have set up, is exactly what Eduardo said, is now that you know this site's good, or more importantly, I think the site's bad, I'm getting excessive call drops or very low throughput in my uplink, which is usually the trigger we'll get from a service provider, is okay, that site's fine. But now we'll take that site as a reference, PCI 150 again, and we'll still give you a relative, an absolute time error. I realize I can't show my mouse on your screen, but we don't equate for distance here because it's ever changing. So now you'll see, instead of it being negative 20 microseconds, was that right? 20 nanoseconds. It's actually 5 microseconds, but we don't really care because we're not equating for distance. So we do show it because we like you guys to see it. But again, that's based on our distance. But this screen, we're using the sync error, which Eduardo's showing here. So we set the one that we know is good as the golden standard, 0. And then we measure every other signal that we can see. And Eduardo's system is static in his office. We're not driving, obviously. And you can see that every once in a while, a second sector or a different site is coming in, and its relative offset is 0.68 microseconds. Let's see if I can freeze the screen. I'm going to try to freeze one so it doesn't jump out of there. I am not fast enough for this, Eduardo. Maybe you are.
No, that's good. I think that
Okay,
gives
I got
good
it.
indication. Yeah.
Yeah. So I just wanted to freeze the screen real quick so you can see it. You can see this one's got a lower power level, which we expect. You can see that its relative or absolute time offset based on ours is 4.14. Run some numbers. It's 0.6 microseconds. Remember, the spec is 1.5 in either direction. And then we throw some extra measurements in there, right? If SINAR is extremely poor, well, that might be an indication that there's something going on or there's some interference in the way, right? We throw some extra bells and whistles in there because we're all RF guys and we like SINAR, we like RSRQ. But simplistic measurements on purpose because TDD is new for a lot of people, and what we're finding with this measurement is you can take it from the UE's point of view before you go and see an alarm, or even after you see an alarm in a system, said service provider, and you don't have to pull out your PTP Grandmaster wire line type tool, right? Something that monitors over the fiber or at the switch. You can see the effects as the user sees it from over the air. So this has become a very powerful tool that indicates, yeah, you got a problem. The drive test alone is brilliant because now we can see where there's spots of issues and then start, breaking the network apart if we find it's not in the radio? What if it's the PTP grandmaster back in your CRAN hub or your remote site where all your DUSs and your BBUs are, right? I guess they're called DUs now. Why break that apart if everything's working in over the air? So it's a good leading indicator to get timing measurements before you break out tools, which we sell. We sell lots of the PTP timing tools. They're very good, but they're intrusive, right? You have to do a lot more to it than just monitor. So, Eduardo, is there anything you'd like to add to this screen or this section?
Very good. Thank you, Dan. Appreciate it.
I appreciate you. I will get it back and get back to the questions, wherever those are. Ooh.
So let me just go back here to my presentation. Probably need to go to the best practices while Dan is helping me with the questions. So in terms of best practices on how, okay, so we found a problem. How can that problem be fixed? Okay, so I just put here a simple process, starting with my time error. So we have a time error, so we have a problem. So the next thing it's going to be, okay, so for example, here I did a time error measurement similar to what you saw. In this specific case, I just had a big problem here. Actually, just for you as a reference, the way that I just mimicked this, because this is not real, but the way that I did it was, instead of lock my instrument to GPS, I let it running on its local oscillator. So basically, the local oscillator that we have here on the instrument is also quartz. That also, it's a kind of a local oscillator of my radio. So just, this is probably gonna be similar to a behavior of the radio if it loses synchronization from the primary reference clock. Basically, it's gonna have this kind of deviation that certainly is gonna be well above my 1.5 microsecond limit. And again, you can see a limit that it's failing, and we said, yeah, just have that fail indicator. So again, so we have a problem. How can that be fixed? We talk about there's two different topologies or ways in which synchronization is being distributed. One is going to be a GPS. So with GPS, if it is GPS, then we can test our GPS. So typically here we have our GPS antenna, and that it has direct connection into my, call it BU, BBU element that is controlling the radio. Now we can actually test for that GPS. So actually we can have that GPS have a direct connection into our instrument and see if the instrument gets signals from the GPS system. In this example here, we've connected into it and we have reception of all my signals. So that basically verifies that the GPS is properly working. We've seen instances that the GPS actually is not sending any alarms, but actually is locked, meaning that is not sending any signal reference to the network element, and the network element then again starts deviating without having any alarm. So this is a good way to troubleshoot for either cables or antenna problems in GPS that might be affecting my radio. Okay, now, but it's not if the distribution is not via GPS, but it's via PTP, a precision time protocol. That reference or that standard is 1588 for you, just to have that connection. PTP and 1588 is the same. So here now the connection is being made of, okay, maybe this GPS antenna exists, maybe doesn't exist, maybe it's just coming directly from my slave clock. And this is what I'm going to be testing. I'm going to be testing the synchronization out of this piece of network element that is been sending timing to multiple elements. This is my sync distribution unit, and that's what I'm going to be testing. And the way in which I'm going to be testing it, it's via packets, it's via data, it's via PTP. So here with our instrument, we're also looking to the protocol, the Ethernet protocol, and we're going to be making tests against, in this case, a GPS And if GPS is not available, which not all the times it's available on a enclosure, on a CO, then certainly we have a timing module that will sustain the stability of GPS indoors. And that basically, that's how we can troubleshoot and make sure that all these synchronization distribution units or slave clocks are providing proper synchronization into my radios. Okay, and with that, I'm going to give you a couple of more references if you're interested in getting a little bit more information about our solutions. But I want to thank you all. We went a little bit over time, but I want to thank you all for the time. And as I mentioned at the beginning, if you still have some questions or comments, please send those over via email. Gloria?
Thank you. Thank you, Eduardo. I think Steve and Dan are answering just a couple of final questions, and we really appreciate the interaction on this session. Thank you all for joining us. I'm going to keep it open for just a little bit. Once I stop the recording, I won't turn the webinar off quite yet to allow those questions to be answered. But as we mentioned at the top of the session, this was the second in our series on uplink interference management. And our third and last session in this series is on Wednesday, April 19th. I've put the link to register for that session in the chat. The topic on that one is external interference, and we'll follow a similar format to this one. And of course, our last webinar, which was on PIM. If you were not able to attend the PIM webinar, please reach out to your account manager for a link, and we'll make sure you know where to find that on our website. It is in our webinars area under on demand for PIM management. But again, we thank you for your time. We hope this was a good time slot for you, trying to cover the US, different time zones and accommodate your schedules. Can be a little challenging at times, but again, if you have any requests about best time of day for these, please let us know. We appreciate your attendance and hope the information was extremely valuable to you. So want to thank you, and I'm going to turn recording off now.